podcast is brought to you by LMU Munich.
Thank you for the introduction, and thank you everybody for being here on such a wonderful summer evening to listen to a lecture on existential physics. What is existential physics, you may wonder? I gave a talk about existential physics at a literature festival last year, or at least this was the title that I sent them. So when I arrived, they gave me a booklet with all the talks from the speakers, and of course, first thing I did was look up my own talk, and I saw that I'd be speaking about the meaning of life. I regret to inform you that I don't know the meaning of life. But I'll do my best to try and explain what I mean by existential physics. I have to admit that when I began learning physics in middle school, I thought it was pretty boring. It was about how pendulums swing, about ideal gases, something with atoms. Useful, no doubt, but it was not particularly inspiring. So when I graduated and went to the university, I didn't go to study physics. I went to study mathematics, for the rather boring reason that I was always good at mathematics. And what intrigued me about mathematics is that it's a very rigorous way of reasoning. It requires very careful definition of the terms, and then you do a logical deduction from your assumptions. This has allowed us to infer a lot of remarkable properties about nature. After a couple of years of studying mathematics, I had to pick a specialization, a particular topic. And it could have been higher algebra or differential geometry, Lie algebras, or number theory, whatever. I couldn't decide what to pick. I thought it was all great. And after a lot of time of thinking about it, I decided I would focus on that part of mathematics that describes nature, which naturally brought me back right to physics. So that's kind of the official story that I tell journalists. The unofficial part of the story is that the Department of Mathematics was broke and they couldn't offer me a job. So they said, go and talk to the physicists. And once I was there, they also gave me a topic for a diploma thesis. One way or the other, I went back to physics, and I realized that what we learn about physics in school isn't the whole story. We get to know physics as something that describes the behavior of matter in space and time. We get to know it as something that applies to inanimate matter. It's about how lights work, atoms decay, rocks fall. But we don't think that it applies to ourselves, unless possibly, you fall off a roof or something, and then the law of gravity does its job. But physics is so much more than this. Physics also tells us something about our own existence, how we fit into this universe. Indeed, I originally wanted to name my new book More Than This, but my editor didn't like it. He wanted to have the word physics in the title, and this is how the book came to be called Existential Physics. And when he came up with this title, I thought, that's great. When I grow up, I want to become a professor of existential physics. The growing up part didn't work out, but the title stuck. So what is existential physics? What do I mean by that? It's physics about those aspects that concern human existence. What changes? Where do we come from? What are we made of? What can we do? What can we know? So it's a very broad spectrum of questions. So that was one part of the reason why I wanted to write this book. The other part is that if you've read anything that I've said or written, it's probably that I've criticized something. Whenever there's a headline saying physicists have created negative mass, or we can do faster than light travel, wormholes, parallel universes, whatever, then I'm the person who has to say, no, they didn't do that. No, that you can't do this. No, they haven't done this. And I think it's kind of important that someone does it, but it's a little bit depressing. And it paints a picture of me that I'm not very comfortable with. I'm always the person who says, no, doesn't work. So I wanted to write a book about what we have learned from physics, all the fascinating things that we have already figured out. So the subject that I wrote the book about is at the somewhat blurry intersection between science, philosophy, and religion, which is where I think the foundations of physics reside. Before I talk about some specific topics that I cover in my book in more detail, I want to put ahead that everything I'm about to say is for all we currently know. So this is according to our best current knowledge about the laws of nature, but maybe, I don't know, next year or in a decade or in a century, those things will change and then the books will have to be rewritten. I put this ahead because when I wrote the book, I noticed that I was constantly writing, for all we currently know, blah, 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 for all we currently know. And in the end, I decided I just put it in the preface and be done with it. So I'm doing the same thing here today. I'll start with the question, does the past still exist? So this is all about Einstein's theories of space and time, about which I could give several-hour lectures, but we don't have that amount of time. So today you'll get the briefest of all brief introductions to Einstein's special relativity. It's basically built on three principles. The speed of light is finite. It's very large, but it's finite. It's the same for all observers, no matter where they are and how they move. And nothing goes faster than the speed of light in vacuum. The speed of light in a medium can depend on the observer. Now that sounds rather innocent, but if you take the mathematics seriously, you can arrive by logical deduction at some very astonishing conclusions. Okay, so the speed of light is finite. It sounds a little bit boring, but think about this for a moment. When you see and hear me speak, you see and hear what happened a fraction of a second in the past. You never see me the way that I am right now. You can't, because it takes a tiny, tiny amount of time for this signal to arrive where you are. And you may say, well, come on, you know, that fraction of a second, who really cares? You know, if I ask, am I here now? What do we even mean by this? What do we mean by now? Why are you asking this question? So it becomes very difficult if you try to figure out what we even mean by now once you take into account that the speed of light is finite. And you might say, well, that's kind of boring. Why are we even talking about this? But let's think about the consequences for a little longer. So this is a thought experiment that goes back to Einstein already. So he said, suppose you're standing on a railway track and there's some cart going by from the left to the right, as you see in this image. And your friend Alice or whoever is on the train. Now, the moment she's directly in front of you, like you're looking directly at her, like you see in this image, there is some kind of trigger mechanism where you see the red arrows that'll flash a light. Now, the question is, do you see those light flashes at the same time, yes or no? Well, for what you're concerned, that's pretty obvious. Forget about the whole train. Who cares about the train? It's just about the light. So by the way that you have arranged this whole setup, both of those light flashes happen at the exact same distance from you. And the speed of light is always the same. So you have two sources of light at the exact same distance from you. Of course, they arrive at you at the same time. So you would say, well, they were simultaneous. They happened at the same time. But how does this look for your friend on the train? Well, so the light flashes, but the train goes a little bit to the side while the light travels. So there's one of those flashes that arrives where she is earlier than the other one. And she would say, well, they're not simultaneous. So did they or did they not happen at the same time? Well, it turns out that the answer depends on the observer. It depends on how they move. Observers who move at different velocities see different things happening at the same time. Now, normally, this is an extremely small effect, so you wouldn't notice it if you walk through the room. But in principle, mathematically, if you walk through the room, you have a different notion of simultaneity than when you stand. This is one of the consequences of Einstein's theory of special relativity. And it's nothing to do with trains in particular. There are other examples that you can look up where you arrive at the same conclusion. So what does it mean? It means that you can talk about your notion of now, like what is happening now for you, but the notion of what happens now elsewhere depends on the observer, depends on how they move. One of the consequences is this, that your past might be somebody else's present, or the other way around. Your present might be somebody else's future, depending on how they move. And if you ask the question for all possible observers in space-time, you realize that there is no possibility to define one moment as now. Every moment in time could be now for someone. The consequence of all this is that once you accept that something like now can happen elsewhere, and not just where you are, you have to accept that all moments in time exist in the same way, like your present moment. So Einstein's theory of relativity does not allow you to distinguish between the past and the future and the present. The only other logical possibility to get around this conclusion is to just deny that you can talk about what happens now elsewhere. So you have this super localized notion of now that only applies for yourself, and then you have to ask, like, which now is it? Which of the synapses in my brain determines the now? So it's not just a quirk of perception. There is just no way to decide what now elsewhere even means without some ambiguous choice of the observer. It doesn't fundamentally make any sense to talk about this now. And this is what we call in physics the block universe. The block universe doesn't come into being. It doesn't have a notion of now that goes forward. It just sits there like a block. Everything is in place already. And that's a consequence of Einstein's theories. Now there's the question, why do we perceive one moment as now, as a special moment? Well, I don't know. I think that's not a question for physics, really. That becomes very difficult to explain what happens in the human brain. Why do we only remember the past and not the future? Yeah, I think I leave this to a neurologist. But at least fundamentally, according to what our theories of nature are concerned, all moments exist in the same way. Now, Einstein, when he wrote down his theory, didn't take into account quantum mechanics because that hadn't been established at the time. So when you take into account quantum mechanics, it becomes a little bit more difficult to talk about the future, and I'll have a little bit more to say about this in a later section. But at least for what the past is concerned, for all we currently know, based on the established theories that describe the universe, the past still exists. There is another way to look at the same question, which is to look at the question whether information can be destroyed. So maybe I should first explain what we mean by information. Information has very different meanings in different areas of science. In physics, what we mean by information is just everything, all the details that you need to describe what's going on. So in the simplest case, when you're talking about shooting an arrow or something, that would be the initial position and the velocity of the arrow, as you learned in kindergarten, I suppose. So that allows you to calculate what happens at any later time. So the information that describes the arrow would be the position and the velocity. The same could be the case for any kind of particle. Quantum mechanics becomes a little bit more difficult, that you have a wave function, but it's the same idea. What we call information is everything you need to describe the wave function. So that's it. I admit it's kind of a little bit vague what we mean by information. It seems to imply more than we really imply when we use the word. But that's basically, it's all this data for the state of the system, whatever that system is that you want to describe. Could be you or your arrow or a bunch of particles, whatever. Now there's a funny thing about the way that we understand the laws of nature. We have this state of the system at one time, which could be the positions and momenta or the wave function or something else entirely. And then we have an equation that we use to calculate how this state changes in time. We call this an evolution law. And then we calculate what happens at later time. But all the laws that we currently have in the foundations of physics, they work forwards and backwards. It's not just that we can take an initial state, like for your arrow, and calculate what happens later where this arrow lands. We could also measure where the arrow lands and just in which angle it hit the ground and with what momentum. And we could use this to calculate where it came from. It works forwards and backwards. We call this time reversibility. So all the laws that we have in the foundations of physics are time reversible. Doesn't mean they work the same way forwards and backwards. Most of the time that's actually not the case. That would be time reversal symmetry, but they are time reversible, so we can run them forwards and backwards. We actually do this in cosmology. If we want to figure out what happened in the early universe, what we do is we take the observations from today, we look at how the universe looks with all the galaxies and stuff, stars and nebula and gases and whatever. And we use those equations to calculate what must have happened in the early universe. And because we can infer from the data that the universe is currently expanding, we can deduce that in the early universe, matter must have been very dense. And this is where the conclusion about the Big Bang comes from, that I'll talk about a little bit in a moment. So we do actually in practice use those evolution laws forwards and backwards. What this means, philosophically speaking, is that information can never be destroyed. It's just reconfigured. Because whatever the final state of your evolution law is, you could, if you had the computational capacity, measure exactly what the state is and calculate where it came from. For practical purposes, this is often not possible, of course. If you burn a book, the theoretical physicists can say, well, theoretically, all the information is in the ashes and in the dust and whatnot, but for practical purposes, that's not particularly helpful. But if you're worried about what happens with all the information that makes you, at least for all what we currently know about those fundamental laws of nature, it can't be destroyed. Except for two things. So there are two exceptions to this in the foundations of physics. One is a measurement in quantum mechanics, and then there's black hole evaporation. So let's look at those in a little bit more detail. So in quantum mechanics, we describe everything by a wave function. You don't really need to know exactly what a wave function is. The only thing you need to know is that from the wave function, we calculate the probabilities of measurement outcomes. We can, in quantum mechanics, not calculate exactly what's going to happen. So if we take, for example, a laser and we direct this at a beam splitter, the beam splitter, as the name says, splits a beam. So if you look at a single particle in that laser beam, a photon, that's a quantum of light, it has a 50-50 chance of either going through the beam splitter or being reflected. Quantum mechanics cannot tell us which is going to happen. It just tells us, well, there's a 50% chance it goes through and a 50% chance it's reflected. And we calculate this from the wave function. That's the role of the wave function. Now, the issue is that the moment we actually measure the particle, it's either left or right. Now we have to update the wave function to reflect this change in probability. So previously it might have been 50-50, but once you've measured the particle, you know it's on the left side with 100% probability. This is often called the collapse of the wave function, or the update or the reduction of the wave function. It's all the same thing. And this is what this sketch is supposed to say. So you had some kind of probability distribution of different positions of your particle. Then you make a measurement, you know where it is. Now the thing is the following. This measurement update is irreversible because you cannot, from the 100% inference of the position after the measurement, figure out what the wave function was before you made the measurement. It could have been 50-50, or could have been 60-40, or it could have been 90-10, and you just got lucky and measured it where it was only a 10. So the measurement update is irreversible. So if that is actually how nature works, then in a measurement update, information actually gets destroyed. Yeah. So measurements in quantum mechanics do destroy information, but the question is, do they really describe what happens? So this is like the big open controversy in the foundations of quantum mechanics. Is the collapse of the wave function a physical process, or is it just a statement about the update of your knowledge? Well, we still don't know. Physicists have been discussing this back and forth for 100 years. George wrote a great book about this. So we still don't have an answer. I hope we'll find one in my lifetime. So if I don't give public lectures, this is what I'm trying to think about. Personally, I think the collapse of the wave function is just a placeholder for a more fundamental underlying process, which eventually will actually be time reversible, but this is very speculative. If you take the measurement process as a fundamental property of nature, then you run in all kinds of problems. For example, it brings up the question, who measures the universe? So you can always ask, well, if I look at the universe as a whole, there's a wave function for the entire universe. Does it ever collapse? And if so, who's doing the measurement? So that doesn't really seem to make a lot of sense. And there are several other problems that are related to the measurement update. For example, if you think about what I told you earlier about the photon going through the beam splitter, 50-50 left or right, the moment you make a measurement, you know that you have to update the wave function on the other side. This is non-local. This is what Einstein referred to as spooky action at a distance, and he didn't like that at all because it happens faster than the speed of light. The reason it's not outright in conflict with Einstein's theories of special and general relativity is that you can't observe it. So in the end, by observations, you can't really figure out what's actually going on, but it certainly gives you kind of an icky feeling, like what's going on with this faster than light thing. So those are all reasons why I think that the measurement process is probably not fundamental, but yeah, other physicists will probably disagree. Okay, so now let's talk a little bit about black holes. Stephen Hawking taught us that black holes don't last. What's happening at a black hole horizon is that the vacuum becomes unstable and it tears space-time apart into particles and antiparticles, and one of them falls into the black hole and the other one escapes. So the energy for this pair of particles is taken from the background, from the gravitational field. So the energy of the gravitational field decays into a pair, one of which goes into the black hole, the other one escapes to infinity, far, far away. So the net result is that the black hole loses mass, and eventually it's entirely gone. Now, that in and by itself wouldn't be a problem, but the thing is that this radiation that comes out of the black hole, which is now called Hawking radiation, after Stephen Hawking, is completely random. The only information that's in this radiation is the temperature. And the temperature itself depends on the mass and the angular momentum and the charge of the black hole. So those three quantities about the black hole that are encoded in the radiation that comes out, but that's it. So if you have a black hole and you throw something in, a stack of books, a turkey, apples, whatever, you make a bigger black hole, the black hole evaporates, And all you're left with is this random radiation. And it doesn't matter exactly what the black hole was formed from. You cannot infer what went into the black hole from the radiation alone. So that process too seems to be irreversible. And this is actually what leads to what's known as the black hole information loss paradox, which Hawking worried about 40 years after he had created the paradox, and eventually it outlived him. So we still have the black hole information loss paradox. The issue is that this black hole evaporation is inconsistent with quantum mechanics because you have this irreversibility already without making a measurement. Even if you don't look at the radiation, it's already not time reversible. Whereas in quantum mechanics, so long as you don't make a measurement, it should still be reversible. So mathematically, the two things just don't fit together. Black hole evaporation and quantum mechanics, they don't cooperate. It's just a mathematical contradiction. So this is what we call the black hole information loss paradox. And again, when I talk about information, as I warned you earlier, in physics, at least in those parts of physics, we use the word very, very loosely. It just means that we cannot infer the initial state from the final state. That's it. So the word is kind of misleading. Now, what's going on? You know, this is like a mathematical inconsistency. This is not how nature works. There's got to be some solution to this. Where most physicists believe, and I'm one of them, that there's something missing in Hawking's calculation and that the process is actually reversible. There are good reasons to think this. The best reason is probably that we don't actually know what's going on inside a black hole. The reason is that if you look at the mathematics, then inside a black hole there's a singularity. That's where the curvature of space-time becomes infinitely large. Now, whenever something becomes infinitely large in physics, that's kind of fishy. Physically real things shouldn't go to infinity. And indeed, if we have singularity, something going to infinity in other areas of science, it's a sign that the mathematics breaks down. We have this, for example, in hydrodynamics, when we're describing fluids. Like think, for example, of a drop of water pinching off the tap. So it falls down slowly, and at the point where it pinches off, there's a very sharp peak. Now, technically, this peak is a singularity in the curvature of the surface of the droplet, comes from the surface tension. But we know that if you were to zoom into this pinch point onto the singularity, what would happen is not that you'd find something actually going to infinity, but eventually you'd start resolving the molecules and then the atoms and then the tinier particles that the atoms are made of. So the only thing that this tells us is that this approximation that we use in hydrodynamics to describe a fluid breaks down. And most physicists think that this is the same reason why we have those singularities inside black holes, and we also have a singularity at the Big Bang. They probably come about for the same reason. The theory that we use to describe those situations, general relativity, actually breaks down. We need a better theory. We need a theory that takes into account the quantum properties of space and time. That's called quantum gravity. But we don't have this theory. String theory is one of the candidates for this theory. There are others. They all have in common that they resolve the singularities and replace them with something else. And in all those approaches, black hole evaporation should eventually be reversible again. Unfortunately, we can't experimentally test it. The issue is that the black holes that we know exist out there in the cosmos, supermassive black holes, solar mass black holes that we have experimental evidence for, they're very large, and the larger the black hole, the smaller the temperature. And those black holes are actually, they're so large that at the moment they don't even evaporate because their temperature is lower than that of the cosmic microwave background radiation. So they would actually gain photons from the cosmic microwave background, except that this is a very small contribution. Normally they gain more mass from gas and other stuff that falls into the black hole. So really, we don't know. So can information get destroyed? Depends on what you believe happens in a measurement in black hole evaporation. I think the answer is no. I think eventually those two processes will turn out to be time reversible as well. Okay, then let's move on. This already came up a few times. How did the universe begin? What's with the Big Bang and all that? So this is how modern cosmology works, basically, in a nutshell. It's based on Einstein's theory of general relativity. It's one of the theories of the type that I talked about earlier. We use an initial state, and then we have an evolution law. In this case, the evolution law, it's what's called Einstein's field equations. They're 10 non-linear coupled differential equations. It's very complicated, but luckily I don't have to explain them today. So what we do is we put in sources of matter and energy into that space-time, and then we can calculate what's going to happen. And what we find is that if you put the stuff that we see around us into the universe, it expands. Okay, so the universe expands is one of the consequences of Einstein's theory. The rate of expansion is determined by the amount of matter and energy in the universe. This is how we can infer stuff like that there's got to be something like dark matter in the universe, there's got to be something like dark energy, but this would be another talk entirely. It does make a lot of predictions. The formation of structures, like how fast do galactic filaments and galaxy clusters and so on form, and how are they distributed, how much do they clump. There's the cosmic microwave background, that's leftover radiation from the early universe. There's the abundance of light atoms in the universe. Those are all predictions from this standard model of cosmology, how it's sometimes called. It's also known as the concordance model or lambda CDM. If you've heard of this, it's all the same thing. So this is the normal, generally accepted description of the universe as a whole at the moment. Now what you can do is you can take those equations and just run them backwards in time and run them backwards. And what eventually happens is that you find a singularity. The curvature goes to infinity. And this doesn't happen at an infinite duration, but it happens at a finite time, about 13.7 billion years in the past. We run into this singularity. And this singularity is what we call the Big Bang. So what's it mean? So we have a singularity. Well, most physicists actually don't think that this is what happened for the same reason that I just explained. We don't actually believe there's a singularity inside black holes. It probably just means that those equations break down. Indeed, normally, there's somewhat, unfortunately, some physicists use the word Big Bang with many different meanings, but most of the time what we mean is whatever's going to replace the singularity in the to-be-found underlying theory. So it's kind of a sliver around this singularity once you've taken it out. This is what we mean by Big Bang. Okay, so that's just what we get out of the equations. And that brings up the question, like, how does this even make sense? Like, how can we do this? Like, remember, so we have the present state of the universe, which for cosmology is actually the final state. We have this evolution law, and this gives us an initial state. But we could take any evolution law and calculate what happened earlier, and that would just give us an initial state. There's always one. So how do we know which one is the right initial state and which one is the right evolution law if I could just use any? So suddenly it looks like we can't possibly say anything about the beginning of the universe. So what are physicists doing? Well, it's a little bit more complicated than that. So what we actually do is we look for an evolution law that makes the initial state as simple as possible. And for most evolution laws, what happens is you take the present state, you take all this data, you calculate what happened earlier in the universe, you get something very, very complicated to make it work out. What's so special about Einstein's theory and his evolution law and the initial state that we currently use with this hot plasma in the early universe is that it explains very simply why we have those observations that fit together in a particular way It gives you the formations of structure, and it gives you the cosmic microwave background, and it gives you the right abundance of atoms. If you were to take a different evolution law, you would have to put all this data by hand into the initial state. So you wouldn't predict anything. You would just put it in and I say, oh, look, I got it out because I put it in. So you wouldn't learn anything. So this is how we select an evolution law together with an initial state. It has to explain something. It has to simplify something. And Einstein's theory is really, really good at this. Now, but this brings up the following possibilities. As I just told you, I can take any evolution law and just run it backward in time. So if I don't like to have this singularity there because that gives me a big bang and I don't want anything like that, I can just change the evolution law if I go backwards. So I use Einstein's theories backwards in time until somewhere when we don't have any data anymore, and then I tack on a different evolution law. You can do this mathematically, you can certainly do this. And people have tried all kinds of different things. You can, for example, replace the Big Bang with a big bounce. In a big bounce scenario, there would have been an earlier universe that collapsed, but it didn't collapse to a singularity, just to a very small thing, and then it expands again and gives rise to the universe that we see around us now. These bounces could also repeat. This gives rise to what's known as a cyclic universe. There are other ideas. For example, it could be that if you go back in time, you don't get a Big Bang singularity, but you get a very, very, very slow phase where everything just becomes slower and slower, 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 and basically runs to a halt. But not at a finite time, but at an infinite amount of time. This is known as asymptotic silence. Then there's something that's called the no boundary proposal, where where time turns into space. So, so this is kind of weird because there isn't really a beginning if you don't have time, right? So originally you only have space, and then at some particular position in that space, time starts to emerge. So this is another possibility. You could have 5-dimensional black holes or string gases or what else? Collisions of high-dimensional membranes. I seem to have forgotten about those. So there are lots of those. And they're all fine for what the data is concerned, because that early in the universe, we don't have any data. So you can just take your evolution law and change it to whatever you want. So I think that all those theories are basically modern tales of creation. You know, we like to tell stories about how the universe might have begun, and with experimental data, with our observations, we can't tell them apart. The problem with all those ideas is that they are necessarily complicated. As Laplace already said, you shouldn't add any parts of your hypotheses that you don't know, that you don't need. You should only use the parts that you need. And the only thing we need to describe our observations are Einstein's field equations that we use in the standard model of cosmology, which is the one that runs into the Big Bang, but we don't have any data there anyway. So this is why I'm absolutely not convinced by any of those theories for the early universe. They're all unnecessarily complicated. They're just contrived. They're stories written in mathematics that physicists make up. That doesn't mean they're wrong. For the most part, they're actually not wrong, because physicists are all smart people and they go to great pains to make sure that their new theories for the beginning of the universe are compatible with all the observations. But we can't tell them apart either. So where do we put them? Is it science? Is it pseudoscience? Is it just wrong? Well, my friend Tim Palmer introduced for situations like this the word ascientific. And I thought, this is completely brilliant. I'm going to steal this word and put it into my book. And now a lot of people think that it was my coinage, but it wasn't. So those ideas are not wrong. They're just not within the realm of science, because there's no observation that we can make to tell them apart. We can't rule them out, we can't confirm them, it's just not possible. So I think you can believe whichever one you like. They're all scientifically equally right or wrong. So how did the universe begin? We don't know, and we may never know. And the reason I say we may never know is that as I already said, the way that our theories work, the only thing we ever do is we push back this initial state. So we look back in time, we choose a different initial state, we look a little bit further back in time, we have some more data, we can push back this initial state a little bit further. But the further back in time we look, the simpler the initial state becomes and the fewer data we have. And I think eventually we'll just run into a situation where this state is as simple as it can possibly be. And that's where our model of cosmology will end. And it might then perfectly well be that there was an earlier phase of the universe that was more complicated. Like there might have been, a universe that actually collapsed and then gave rise to ours. But since this would be a more complicated story than this simple intermediate phase, we'd have no rationale to say it's correct. It wouldn't be compatible with the way that we currently use the scientific method. Okay, now let's talk about something a little more fun. Do copies of us exist? So I think at this point, I think everyone has heard about the multiverse. That's the idea that our universe isn't the only one, but there are other universes out there. They might be very similar to our own, or they might be completely different. It's become very popular with Hollywood. Lots of books have been written about it. And it's certainly very entertaining, but what does science say about it? Well, there's a reason that those ideas have become so popular. It's that scientists actually talk about them, and, not a lot, but sometimes. And there are different kinds of multiverses that have popped up in the scientific literature. The probably least controversial of them is what's called eternal inflation. So what we mean by inflation in the context of the entire universe is that in the very beginning of the universe, it expanded very rapidly, exponentially. And this phase of rapid expansion is called inflation. Now, so far so good, you might say. Now, the thing is that the current theory for how this phase of inflation began has it that the universe was filled with a quantum field that's called the inflaton. And this quantum field made a lot of fluctuations. One of those fluctuations began to expand exponentially, and that eventually gave rise to our universe. But there wasn't just one fluctuation in this quantum field. There are actually infinitely many. And any one of those fluctuations can give rise to its own universe. So the argument goes, well, once you believe this thing with the quantum fluctuations in the inflaton field, for which we don't really have any evidence, but it's there in the mathematics, then you also have to believe that these infinitely many other universes exist. And they could possibly have different constants of nature. This is sometimes called the landscape. This is an idea which comes from string theory. So different constant of nature could be, the masses of elementary particles like the electron, or it could be the strength of the electromagnetic interaction, or the strength of gravity, the speed of light, stuff like this. So all those constants could be different in those other universes. The problem is, there is no observation that can refute or confirm that these copies exist, because we're completely causally disconnected from all of those other universes. There's no way we can interact with them, and we can never figure out what's going on. This isn't the only type of multiverse. There are actually, you can say, a somewhat more innocent version of the multiverse is if you believe that our universe is infinitely large, and all our planet and solar system and all other solar systems grew out of fluctuations in this very dense plasma in the early universe, then all those fluctuations should repeat in other places in this infinitely large space. Because if you have an infinitely large space, anything that can happen will eventually happen somewhere. And actually it'll happen infinitely often in all possible tiny modifications that you can think of. So there are infinitely many copies of the solar system out there, with infinitely many copies of all of us, with possibly small modifications. On some of those planets, there's a copy of you which won a Nobel Prize. In another copy, you're a ballet dancer. or maybe you're a singer, a rock star. Everything you ever wanted to be, there is a copy somewhere in this infinitely large universe where you did it. Well, the problem is there's no observation that can refute or confirm that these copies exist. It's all well and fine to say, well, technically, mathematically, you know, I can write it down and it should exist, but there's no way that we can ever get there. To add one final version of the multiverse, though there are more of those, but you know, I don't want to talk forever. So probably one of the best known ones is the many worlds interpretation in quantum mechanics. So as I said earlier, in quantum mechanics we have this problem with the measurement process, that when we make a measurement, the wave function changes instantaneously everywhere. So this is the collapse of the wave function. It's non-local. Einstein didn't like it. Spooky action at a distance, blah, 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 blah. So now one way to solve this problem is to say, well, maybe the collapse never happens. Instead, what happens is that the universe splits. So instead of saying, well, the photon went through the beam splitter, 50% left, 50% right, and then I make a measurement and now it's 100% on the one side, you can say, well, in one universe it was 100% on the left side, in the other universe it was 100% on the other side. Now you have two universes, one for each possible measurement outcome. And the same thing happens every time there is a quantum measurement. Now, what we mean by quantum measurement actually doesn't necessarily have something to do with an apparatus. You know, quantum measurement happens each time a photon hits a wall. So there are lots of those measurements, and there are infinitely many of those splits have already happened. They're constantly happening all the time, everywhere. So that's a really, really big multiverse. Now, you saw it coming. The problem is that there are no observations that can refute or confirm that these copies exist. Because for what our observations are concerned, we only ever see one outcome of the measurement. It's all well and fine to say, well, there's a parallel universe in which the other outcome happened, but what does it mean if you can't observe it? So I think what's going on there is that physicists got a little bit confused about the reality that they assign to their equations. Just because there's maths for it doesn't mean it's real. You can assume that it's real, but if you do this, that's an unnecessary hypothesis. So you shouldn't do it. It wouldn't be science. So science can't tell you that those other universes with those copies of us are real. But it can also not tell you that they're not real, because there are no observations you can make. So what does it mean? Well, it means it's an ascientific idea. You can believe it if you want to. Nothing speaks against it, but nothing speaks for it either. Okay, so one final question that I have for today: can particles think? This is a question I had to debate with several philosophers over the course of years. It usually did not go particularly well, but I learned a lot along the way. So this is an idea which goes under the name panpsychism. So the idea is that everything is a little bit conscious, like everything, like elementary particles, tables, wood, what have you, carrots. Everything has a little bit of consciousness, but normally it's so small amounts of consciousness you don't notice. That's why carrots don't talk to you. But this proto-consciousness, as they call it, can combine to larger amounts of consciousness, and at some point there emerges something that can walk and talk and give semi-coherent talks. So this is the idea how in a panpsychic universe conscious beings come about. It's just because they collect this proto-consciousness. Now, there are two versions of this panpsychism. In the one, this proto-consciousness is a physical stuff, and in the other one it isn't. So in the case when it isn't physically real, then this is just dualism. Okay, you say, well, there's something that I call consciousness. It doesn't have any physical reality, but I just choose to believe in it, and I think that this explains something. This is all well and fine. If you like that idea, feel free to believe it, but it doesn't really explain anything, because now you've put it out of the physical universe. You can't use it to actually explain something in the physical universe. Okay, so I would say this is an ascientific idea. It's fine, believe it if you want. Then there is the other option, that the consciousness stuff is physically real. Now the issue is, once you make this proto-consciousness physically real, then it has to agree with what we actually know about physics. And this turns out to be surprisingly difficult to make work. So here's the standard model of particle physics, contains 25 particles. You don't have to count them, I counted them for you. Some of them are good old friends, like the electron and the muon. Probably you've heard of those. There's the Higgs boson. The Higgs boson was the last one to be discovered at CERN in 2012. And all those particles are classified by what we call quantum numbers. Quantum numbers are just what the name says, they're numbers, like they're values like 1/2, 3, 5/2, something like this. So it's just a bunch of numbers for things like the electric charge, the weak hypercharge, the spin, and there's a whole set of those numbers. Now the point is that if I give you this set of quantum numbers, you know exactly what the particle is. And that's basically what the standard model of particle physics is, a collection of those numbers that quantify the properties of those particles. Now, why do those numbers matter? It's because if you have the quantum numbers, you can calculate what the particles do, for example, when they collide. So this is why we build particle colliders, because we want to slam those things into each other and see how they decay. So what you see in this fancy image there, this is a collision recorded at the ATLAS experiment at CERN. So the two beams that collide there go into the slide direction. And then those beams run into each other, so there are protons in the beams, and they create all kinds of new particles, which are those black tracks that you see in this figure. And then on the outside, you see a detector where you have all those peaks, and you're trying to reconstruct exactly what went on in this collision. Now, we use the mathematics of the standard model to make predictions for what happens in those collisions. For example, we calculate something that's called the multiplicity, that tells you basically the amount of certain types of particles that are created in this collision. It's like the most obvious thing that you can calculate. There are more complicated things than you can calculate. And the point is, they all depend on those quantum numbers. So the only thing you need are the quantum numbers, and that'll give you a result. Now the thing is, if you add any other properties to those particles, doesn't matter how you call it, could be consciousness, you could call it applesauce, doesn't really matter. You quantify it, you change something about the standard model, you'll change the number of particles that are created in this collision. This is how we know that elementary particles, electrons, muons, Higgs, and so on, they cannot have any other properties than the ones that are in the standard model. It's not compatible with the data. So it doesn't really matter what exactly you think it means for an electron to have consciousness. We know that it can't have any physically real consequences, because we would have seen that already in those particles collisions at the Large Hadron Collider. So this is an example where it's actually possible to rule something out, which I find pretty exciting. Do particles think? No, they don't think. Yeah, so in my book I have several other questions that I think are pretty exciting. Why doesn't anyone ever get younger? This is all about entropy. How will the universe end? Was the universe made especially for us? This is this question of fine-tuning. What do we mean by explaining something that I just jumped over today? So you can find all this in my book. Und das gibt's jetzt auch in Deutsch and in Chinese, which I think is very interesting, and probably soon in several other languages. Thank you for your attention.